this. I'm going to jump right in and start my talk. And this first part I called Think in Distributions. And to give you an overview of different statistical concepts, I'm going to actually jump right in and tell you about a company. I'll be using this to guide our talk today. So this company is called Banana Bio, and it was one of the hottest companies making the rounds a few years ago. And there's a great team from top universities. And when they were in academia, the team had independently discovered this new biological phenomenon, something called the banana factor. And it turns out that cells use bananas to send messages to each other across the entire body. And each banana is like a chunk of code. A cell eats them and then decodes the message within. And this was a Nobel Prize winning discovery. I'm sure the biologists in the presentation know exactly what I'm talking about. This is referring to something real, not bananas. Well, the company found a way to capture these bananas, decode them in the lab, and then use them to diagnose disease. And what they found was astonishing. So it turns out that bananas could be used to detect many types of cancers. And even if you go outside of cancer, they could be used to detect diseases like lupus, which is a very complicated disease. And the company was able to make diagnostic tests with near perfect AUCs across all of these different areas. And the company was, as you can see, showing off their data in this shot in their pitch. But as the title implies here, amazing numbers can be deceiving. And in this session, I'm going to use a company as an example to walk through why numbers might be deceiving, what you should look out for. And along the way, hopefully I can describe some basic statistical concepts. For example, to understand what an AUC is, you must first understand what a ROC curve is. And then to do that, you need to understand sensitivity and specificity, which you need other concepts to consider. So this is going to be fun. Let me quickly introduce myself and do a proper introduction. So, my name is Noel, but how do you know that I'm not spouting nonsense, right? So Seth and Ella mentioned that I have a PhD in something sciencey. It's chemical biology, but it's just a science PhD. It's not a statistics PhD. I did take one statistics class in college. It was an upper level class, but that was 10 years ago. So how much that actually matters, I don't know. I'll let you decide. I think the biggest thing that you can think about of adding credibility to what I'm about to say is that I have 4-ish, less than 4, but almost years of evaluating startups with Illumina Ventures. Now, some disclaimers here, because I have to include these, right? All examples are made up or blinded. If something seems like a real company, it's not. It's an amalgam of all these different companies I've seen over the past. None of this is investment advice, nor it's not advice to invest in a company, nor is it not to invest into a company. So please do not think that I'm referring to any sort of investment. And all views are my own, don't represent the employer. And everything that I draw here is illustrative, but nothing is to scale. So just keep that in mind. I've drawn a lot of the data that I'm going to present. And the last thing is that this is not a statistics class, right? What I'm trying to present are statistical concepts as applied to technical diligence. To do that, if you want an actual statistical class overview, I'd say check out some videos on YouTube, and I can even send around some links after the seminar is over, detailing some good resources. I'm told that most of the attendees here are investors. So I have designed the lectures with investors in mind, but I think the concepts are generally applicable to most people. And then the last thing I want to say is that the title of this talk is about statistical literacy and deep tech, but clearly I'm a biotech guy. A lot of my examples are going to skew biotech. All right, to really understand statistical concepts, let's start with a framework. And you guessed it, it's thinking in distributions. I'm going to be thorough, so I will walk through the basics, and please bear with me. I know that this is probably review for the vast majority of participants, but it's good to start at the beginning. So this is a normal distribution. And typically, when you think about data sets, you think about them as distributions. And you can have a left skew or a right skew for distributions. I used to actually get this concept confused because the bump is on the left, but the tail is on the right. So the way I think about skews now is thinking about pinching this part of a normal distribution and then pulling it to the right or the left. If you pull it to the right, it's a right skew. If you pull it to the left, it's a left skew. For a normal distribution, the mean, median, and mode all kind of center around the distribution. But as you skew the data, you are dragging the mean, median to the right or the left, depending on the skew. And that kind of makes sense, right? Because for a normal distribution, you have an equal number of parts to the left and the right. But when you have a skew, you now have more numbers. For example, with this right skew, you have more numbers that are higher. And so, of course, the average is going to be higher. And so you're pulling the mean and median to the right. There's a lot of different types of distributions, and I'm not going to talk about most of them or any of them really, because these are useful things to know, but they're not going to be useful for the talk. I would say that if you are interested in the many different types of distributions that you see, please look them up online. There's a lot of great resources out there talking about the 20 or 30 different distributions that are typical. One thing I will mention is that when you think about a normal distribution, especially in kind of technology, you hear about Poisson or Gaussian. The only difference between those are typically normal distributions. The Poisson distribution is typically discrete numbers versus a Gaussian is contiguous. And so that's all. Poisson you think about as bins, and then Gaussian is something that's contiguous. And the other thing to remember is that while we think of a smooth curve when viewing data as distributions, the underlying data that actually bring rise to the curve itself is actually quite messy, right? This seems quite perfect, but in reality, data looks like this. Almost all startups and entrepreneurs are dealing with messy data and fitting a distribution curve to the messy data set. And so we have to remember that even if we think in distributions like this, that the underlying data is messy and it's not going to be perfect in the statistical applications. And obviously, this is a framework and it's useful when thinking about statistical concepts, but it's not applicable everywhere. So just keep that in mind. All right, so I think I've talked about that enough. Let's talk about sensitivity and specificity, which should be thought of as distributions of healthy people and diseased people. All right, so here's two normal distribution curves, one of healthy and one of diseased. So we'll call these true negatives for the ones that are healthy, because if you're healthy, you do not have disease, you're negative for the disease, and true positive if you are diseased. Now the distributions overlap, and so we need to set a threshold in which we want to call things diseased or healthy. So if you set a threshold down the middle where the two curves overlap, everyone to the left of the line you would call healthy, and everyone to the right of the line you would call diseased. And that makes parts of these distributions misclassified as false negatives and false positives, right? Because for this blue curve of diseased patients, even if you're calling everyone to the left of this line as healthy, then it's a false negative because they are actually diseased people that you are calling healthy, and vice versa. Now, if the way that you think about sensitivity and specificity is by looking at the fraction of the true positives versus a whole diseased population. And as you can see, if you set the threshold line here, then your sensitivity, which is a true positives over the whole population, is only this part of the area. And it does not count this part of the area here, which is a false negatives. And it's the same thing for specificity, except now for the green distribution, right? It's actually not that hard to think about it when you think of the data like this and sensitivity and specificity like this. And I got a lot of questions from people who applied for the seminar. How come you always have to trade off between sensitivity and specificity? Well, this is exactly the reason. Sensitivity and specificity is based on this threshold that you set. And so if you move this threshold to the left, and let's say you want to get a perfect sensitivity, so now if you move the threshold to the left and all of your true positives are to the right, that means that everyone to the right of this threshold you call a positive, right? So you're going to have 100% true positives because the entire distribution is captured to the right of that threshold. And so as you've increased sensitivity, but you've necessarily had to decrease specificity now because you've also captured way more false positives because you have a lot of healthy individuals that are now being called diseased. And if you think about distributions that are overlapping and thresholds that are moving to the left and right, then you understand why there has to be a trade-off between sensitivity and specificity. And what goes into determining these curves are the data that people use, in our case, companies use, to determine who's healthy and who's diseased. And if you think about technologies and what they do, the way that you get better sensitivity and specificity is by changing what the actual distributions look like. You're changing the distributions to decrease the trade-offs when you're changing the thresholds. And in the case of Banana Bio, they used a lot of different biomarkers like DNA, RNA, and this banana factor, and they fed it into some fancy algorithm, and all that at the end of the day gave them something that looks more like this. So we understand sensitivity and specificity. So let's move on to the ROC curves. So a ROC curve is completely related to sensitivity and specificity. The concept is actually quite simple. If you're graphing out all the possible sensitivities and specificities that change as you change the threshold from 100% sensitivity to 100% specificity and graph that on a curve, that is a ROC curve. That's it. ROC stands for relative operator characteristic, if you care about that kind of stuff. On the curve, so basically on the y-axis, you have the true positivity rate, which is the sensitivity. And on the x-axis, you have the 1 minus specificity or the false positivity rate. And as you can imagine, if you have perfect sensitivity and specificity, your line just jumps to 1 and then moves to the right, which means your AUC, the area under the curve, is 1. If you had two distributions that are completely overlapping, so you have no idea how to distinguish between the healthy and the diseased population, then you get this line here, this diagonal line, which is a random classifier. This is as bad as it can get. Usually what you see is that companies have lines that are somewhere in between the perfect and the random. And you want to move your curves closer to the perfect classifier if you want to have great data. Now that's great. It's quite easy to see now what a ROC curve is and how you calculate AUC. Literally, it's just the area under these curves and why a perfect AUC is 1. So you can imagine what the ROC curve for Banana Bio looks like if they throw out numbers like this, a 0.97, 0.94. You're going to have a curve that is near perfect. But be careful when a company talks about AUCs. They're a great substitute for not having to talk about sensitivity and specificity. And yes, if the numbers aren't close to perfect, then maybe that's fine. But most times the numbers aren't perfect, right? You're talking about AUCs that are not 1, that are more like 0.7, 0.8, 0.9. And sometimes the shape of the curve actually matters and the AUC matters a little bit less. For example, if your distributions look like this in how you're separating your healthy versus disease, then all of a sudden the actual curve itself looks different, right? The area under the curve for both of these might be the same, but one will have higher sensitivity versus specificity and the other vice versa. And depending on the actual scenario, you might want to emphasize sensitivity or specificity. And we'll talk about that towards the end of this particular session. But while you always want to have high sensitivity and specificity, sometimes you can't. Sometimes you have to trade off. And there are real world applications in which one's more important than the other. But again, in the case of Banana Bio, it's hard to imagine that there's any room for shenanigans. And if you look at their actual curve, it is near perfect, right? This is, I drew this, but this is basically what it looked like, an AUC of 0.97, near perfect. So their sensitivity was high, their specificity was high, and thus their AUC was really high. But of course, I wouldn't use this example if there wasn't some sort of twist, right? So the twist here is that this company, Banana Bio, was measuring not just banana factors, but other biomarkers. Because why wouldn't you? If we unpack what the company told us, and we know that they're using multiple things, and they're measuring other known hallmarks of the disease, I would say, that makes perfect sense. Why not use everything at your disposal to make the best test possible? Well, if you look at the data that's buried in the background, this is what they presented. This is stuff that was hidden in their kind of supplemental data, not even in the data room. It was buried in some paper that they had published a long time ago. It's not as pretty of a picture. It turns out that RNA alone gave you a pretty good AUC of 0.94, and the banana factor alone was pretty terrible at 0.6, which means that in combination, the bananas only increased the absolute AUC by 0.03, right? And if you think of these as percentages, an absolute increase of 3%. I mean, who cares about 3%? Maybe some people do, and we'll talk about that as well. But here's the thing, right? Deconstructing the data was necessary to find out what was hidden, but it's not sufficient, because when you think about something like a minimal difference, like a 0.94 to 0.97, maybe it actually is something that doctors care about. Maybe it's a big enough of a jump that it actually changes how people care for patients. Well, they don't, and it doesn't change anything. But if it was, then that would be something. And if it was important, then deconstructing the data can actually lead you to ask other questions as well. Like, when I looked at this data, I thought, why the hell is this RNA curve so good? Is that true? What does the literature say? And what does the actual sample look like? This N of 80 that the company mentioned. So that topic's actually something that we're going to discuss in the next session. But there's a lot of things, additional questions that come up when you deconstruct the data. And I said it's necessary but not sufficient because there are other things you need to dig into. And by the way, we didn't invest in Banana Bio, which is not a real company, but there are companies like this that we saw. Okay, so we talked about sensitivity and specificity and what AUCs mean and all that. Let's move beyond sensitivity and specificity. But before I start, here is the 2x2 that people use to calculate sensitivity and specificity. I'm not going to dwell on this. You can take a screenshot or look at it later when the slides are sent out and study it on your own time, but it's quite simple. Let me just walk through an example. So sensitivity is, sensitivity is a percentage of true positives in the distribution of all diseased people, and specificity is true negatives, right? I talked about that before. To calculate that, you're just looking down the vertical columns here. So this is a real example with COVID testing, and it's based on antibody testing. You can look this up at this link down here. So a company might present this data on the right, showing the results of tests that they've collected for 1 million people, right? This is a total number of people that they tested. Well, you would have pretty good sensitivity and specificity, right? Because here you're looking at the total number of positives that tested positive amongst the entire disease population. So there's 50,000 diseased people, and 46,900 of them tested positive. Great sensitivity, and the specificity is great as well. There's a lot more people that tested negative, but only a few tested positive that are actually healthy. So high sensitivity, high specificity, everything looks great, right? Well, no, because you can't talk about sensitivity and specificity without thinking about positive and negative predictive values, which is completely different, right? Sensitivity and specificity are ways of thinking about the actual test and how accurate a test might be at predicting something. When you think about positive predictive value and negative predictive value, which are calculated horizontally here, this is now thinking about what happens after you get a result. So the positive predictive value is a probability that somebody who actually tests positive is positive for the disease, and ditto for the negative predictive value. If you look at this example and do the calculation, the positive predictive value is only 53%, right? You can tell just because this is 47,000 versus 42,000, they're about equal. So 53% positive predictive value. That means that if you got the test, you only have a 53% chance that you actually have COVID. And the reason why that is because the positive predictive values is dependent on the actual prevalence of a disease. We think COVID is rampant, but actually it's only a small percentage of the population that gets it at any given time, right? And so because the prevalence is low, the numbers of people who are not diseased are much higher than the number of people that are diseased in 1 million patients that you would test. And even if the specificity is great, because here we're talking about people who tested positive, the number of people who tested positive might be the same, because here it's a large fraction of a small number of people, 50,000. Here it's a small fraction of a large number of people, 950,000. So even with a great specificity, you have a large number of patients in this false positive box, and that's what leads to this value. And it's a real problem with things like COVID testing, and it's part of the reason why people argue that they can give you a false sense of security. If I got a positive COVID test and it's a coin flip whether I really have the disease or not, then how useful is that in really determining whether or not I should go back to work or go meet family, etc. Full disclaimer, I think you should still get tested and maybe get tested twice, because then you're compounding the ability for a predictive value. But this is real, and this is something that we deal with today. So great numbers can still lead to a useless test. If you're just thinking about sensitivity and specificity without the whole context of what's happening, then that's an issue. For example, this is an example of COVID testing, but this positive predictive value would change drastically if you tested a million people in New York City in May, where you probably have a much higher prevalence than you do today or back in February. If I could give you a slightly different example, if you apply this test to cancer, for example, right? And you had this type of sensitivity and specificity, you know that the rate of cancer is actually pretty low. So you would end up with a pretty crappy positive predictive value. But that's actually not so bad depending on what type of cancer test you want to have. If you have a cancer screening test, for example, then it doesn't matter that much that your positive predictive value is only 50%, because the patients who test positive will probably go on to get confirmatory testing through some other expensive diagnostic. What is nice to see for this type of test applied to cancer is that the negative predictive value is really high. If you get a false, or if you get a negative on a test, chances are you don't have cancer. And so this is great for screening. It's not great for diagnosis. And so you always have to consider what's the purpose of the diagnostic that a company is making, because these numbers all could be good or bad, just it depends on the whole picture. All right, I'm gonna finish the science part of this by walking through a real example that's relevant to today's pandemic. So this is a SARS-CoV-2 virus, and some of the more important components of the virus that you may have read about over the past few months. And clearly the title's an homage to the season, so I thought a Santa hat was fitting. And also it looks like we might be getting a vaccine for the Christmas season, which is nice. Well, if you look at the SARS-CoV-2 virus, there's all these different types of proteins that are important. For example, this spike protein here is what's being targeted by the early vaccines, like the Moderna vaccine, which maybe I'll describe if we have time later. But let me talk about the actual testing for COVID, right? So there's 3 general types of tests: a PCR test, antigen test, and an antibody test. And for the non-scientists in the group, I'm assuming that there are some non-scientists, a PCR test actually looks for the genetic material. So in this case, this is an RNA virus. So it looks for the RNA of a COVID virus, creates a DNA library, and then amplifies that DNA library for downstream detection. Antigen testing is something slightly different. Instead of looking for the genetic material, you're looking for actual protein components of the virus itself, usually that are broken down. So you have synthetic antibodies that are detecting components of the virus itself, and then you are detecting those downstream. One of the key differences here is that because one is using nucleic acids and genetic material, and one is using proteins, PCR enables you to amplify the signal, which is why you have a higher sensitivity and specificity, versus antigen testing. You can't really amplify the level of protein that you see. You can amplify a signal downstream, but you can't amplify the protein itself, which is typically why antigen tests have lower sensitivity. The third type I'm not going to talk too much about, but it's an antibody test. These are not really used right now because it takes you roughly 1 or 2 weeks to develop antibodies, which is what this test measures, your actual immune response to the COVID virus. And because it takes a week or two for you to develop antibodies, it's not great for an acute setting. If you think you got exposed and you want to know if you have the virus, this is not the best test. You're going to have to wait 2 weeks before you take this test. So just talking about these two, typically the PCR test has a sensitivity above 90%, and typically an antigen test has sensitivity that's 80% or higher. It could be higher than that, but typically PCR is the gold standard because it has a higher sensitivity. Now, this company developed an antigen test, and they claimed that it had 96% sensitivity, but real-world testing, because it's been around and was authorized by the FDA, found that it was more like 80%. Right? Still, there are trade-offs that make it worth it, right? A 15 to 30-minute turnaround time, which is much better than the 1 to 2 days you have to wait for a PCR at half of the cost. I've taken a few PCR tests, and whenever my health insurance doesn't cover it, it's more than $100. So now we're talking about $50, which is much more affordable both to people and to companies that employ them. But let's think about some of the things we just learned and unpack these numbers. So if we look at the sensitivity number of 80% in real world testing, how is that derived? Well, it turns out that this 80% means patients who tested positive with PCR. I just mentioned that PCR has a sensitivity itself of 90% or higher, but it's not perfect. And so this is a big thing to consider when you think about companies coming in saying that we have sensitivity and specificity. What are they actually comparing to, and what is the standard? What is the true positive, and how do they determine it? Because it can be a relative phrase. For people who are developing PCR tests, usually what they're using are spike in RNAs that they're detecting, so you can measure. You know that it's there in a sample because you put it in there, and then you're measuring the technical accuracy of a test. In this case, the sensitivity was measured by comparing to actual patients who tested positive with PCR. So there's some wiggle room in that number is what I'm saying. And then the second thing to think about is who was in the sample, right? In this case, symptomatic patients were tested with this test. But the independent group found that if you test asymptomatic patients, then the sensitivity is reduced below 40%. Basically, it becomes just a worthless test. You have to, the way that you derive a high sensitivity rate, like 80%, or as a company claimed 96%, you just pick the right types of people, and we'll talk about sample selection in the next session. But if you pick the right types of people, then you can blow up your numbers to look like something much better than it actually might be in a real world setting. Now, did we invest in this company or not? I mean, I didn't, because this is a public company. So this company is called Quidel. They've sold a ton of these instruments and tests to different hospitals across the country. And the University of Arizona did an independent study to actually measure the sensitivity in different patient populations. The paper is not published yet, but the New York Times did an expose. There's a lot more to this story that I think is quite interesting. You should look it up on the New York Times and read through it when you have a chance. All right, just to finish off, I wanted to say that sometimes numbers actually mean nothing, right? So Seth alluded to something called accuracy at the beginning. And accuracy is a number that always sounds better than it actually is. It's defined here as all the true positives and true negatives divided by all the tests. Sounds great, but if you had 100 tests and 90 of those were true positives and you detected 0 of the true negatives, you would still have a 90% accuracy even though your specificity was 0. And so you have to be careful when companies, and not just companies, but like people are just talking about testing, and a lot of times they throw around this accuracy term. The accuracy term a lot of times means absolutely nothing. This is another fun thing that I like to always point out, but a combined teamed experience is something you see almost on every presentation. Well, maybe not all presentations, but I've seen it a lot. Another number that means absolutely nothing. What does a combined experience of 67 years actually mean? Does that mean anything? Does it come anywhere near a single person with 67 years of experience? I think not. It's an absolute garbage number. And startup teams, I would say, should tout why each member of the team is relevant versus trying to put up numbers like this. Because sometimes just having experience isn't really as relevant as having someone who's smart and young and someone who's thought about this problem a lot. And this exact example was pointed out in this book that I recommend everybody reads, called How to Lie with Statistics, published in 1954. This author's example was about a publishing company who said they had like 200 collective years of experience by adding everyone's age on the team. So people are still doing this today, and it was around more than 50 years ago, which I think is quite funny. And just to show that numbers mean nothing, in this book, he gives an example of children who ask for more vacation days, starting off and using math to basically say that they deserve more vacation. You can start off with 365 days in the year, subtract out all the time that you spend sleeping, which is a third of the day, subtract the time eating, 3 hours a day, subtract the 3 months of summer vacation, the 3 weeks of regular vacation that you get, subtract the weekends, and all of a sudden you're at negative 15 days and the school owes them 15 days. You have to be very careful about numbers and what people are trying to tell you, because a lot of time great looking numbers mean absolutely nothing. I'm gonna just end the seminar here. Everyone's probably seen this quote. One funny thing to point out here, this quote attributed to Mark Twain, this was actually in his biography or autobiography, but this was Mark Twain quoting Benjamin Disraeli, and it turns out Benjamin Disraeli never actually said this. So sometimes words are deceptive too. All right, I'm gonna stop and let's have a break.